Welcome everybody to this third lecture in our course on pattern recognition. And here is what we are going to do today. I will try, as always, to briefly recap or remind ourselves as to what we have been doing last time. And then I will try to formalize the problem of pattern recognition. Once we are through that, I will point out the requirements we need to have in order to be able to build an automatic pattern recognition system. And finally, I will already today at this point in the course point out how to do it, how to actually build an automatic pattern recognition system. And of course, I will not go into details there, so we'll not learn how to do that, but we will nevertheless learn about a really important fact in the context of building an automatic pattern recognition system. And you will see what I mean once we get there. And probably I should start with a disclaimer. Admittedly, among all the lectures in this course, I consider this one to be the most boring one. And that is because the attempt of a formalization of the problem of pattern recognition basically boils down to me throwing a lot of definitions, terms, concepts in front of you, and well, you have to just sit through it, listen to what I have to say, and I'll point out when it's important to wake up, all right? So let's go for it. I hope it will not be that horrible. Let's see. Our question is, at this point still, what is pattern recognition? I've said it a couple of times already. Basically, three kinds of tasks: regression, clustering, and classification. And in the last lecture, we have seen lots of examples as to the amazing capabilities of the human brain when it comes to these tasks. We actually went through some of them in practice, and you solved them, and it was no problem for you at all. And at the very end of the last lecture, we already tried to make it more precise or more formal, to say what is a pattern recognition system, and the approach I've chosen there was to, just go through, I don't know how many, it was like 10 quotes from textbooks written by people who are prestigious or well-renowned pattern recognition researchers. And in these quotes, we then did some word count statistics, and it appears that pattern recognition seems to have to do with something that's called category, decision, class, name. That was a group of terms that occurred quite frequently in these quotes. Measurement, signal, object, observation, data, just as prominent. Then there were terms like classification and assignment. Interestingly, at least from my point of view, the buzzwords mathematics, algorithm, and function were not as prominent, as well as the word automatic and the term representation. And I'll just wait until everybody has found their place. Please go ahead. And all of this is, of course, not really defining what pattern recognition is. It was just looking at, feelings of people as to what it may be. And so today, I will try to formalize that. In this discussion, I more or less follow the train of thought or methodology of Niemann, one of the people I recommended when it came to textbooks. And I'll actually basically follow his initial chapter there. And again, this will be just lots of terms and an attempt of trying to make sense of these terms. So lean back and listen as to what there is to come. Is this a definition? When we say that with respect to perception, the environment or universe is the entirety of physically measurable quantities of objects or events. So the important word is actually perception, even though I have shown environment and universe in red, because environment or universe is what I'm defining here. But the thing we have to keep in mind is that the problem of recognizing something means to have some sort of observation as to that thing. We need to have some form of perception. And even though the universe is quite extensive and comprehensive, it may as well be that we are not able to physically measure everything. I really don't know. Practically, for all intents and purposes, it doesn't make a difference because, we as human beings, we see, we hear, we taste, we feel, we are able to have perceptual impressions as to the universe, basically to the universe that locally surrounds us. But of course we can gaze up to the stars and see that the universe is much larger than our local surrounding. But we can see stars, we can see this room, we can feel the furniture in this room. So there's lots of things we measure about the universe that surrounds us. Important thing is that technically, so for about the last 100 years, humankind has of course made tremendous progress. We are now able to measure much more things than are accessible to our human senses. So we can sort of look into the very small and look into the very far using microscopes or telescopes. So there are a lot of things we can physically measure, and the entirety of these things we can measure, whether it's with our perceptual apparatus or some technical gadgets. The entirety of these things is called the universe. If there is something out there in the universe, using the term in the sense we usually use, that we cannot measure, well then it is not perceptible to us, and it would not be a member of this set. And a notation. The universe is the set of all functions H, superscript J of O, where J is a natural number, so it's basically infinitely many things. I look at this, this is not a definition, because I don't really say what H is, I don't say what O is. I can think of this as a continuum that contains everything we ever may measure about objects or events. It does not really specify what objects are. What it apparently says is that there are a lot of things we can think of some function. If we take a picture with a camera, it's actually a mapping of the world onto a 2D plane. So these are functions, but this is not a definition. And as we'll see, this problem is systematic. But here are examples of things we can measure, right? I mean, this here says nothing. This says nothing. And whenever we are dealing with something that says nothing, a good idea is to try to come up with something that is concrete, that would fit into that nothing. So the size of an object could be one thing we may perceive. That could be one of these functions JH. The density of an object, whatever that is, a picture of an object, already talked about that, is another possible measurement we can have with respect to the perceivable universe. But of course, sound is also a physical quality that we nowadays can record and measure. Our ears could do that for basically all of history of humankind. Now we can also do this automatically. We can not just take a picture, but a sequence of pictures. And in those sequences of pictures, we may not just be able to identify objects, but actually events. And again, what is an event? Very difficult to define. And this list continues until all eternity. Right? But this is just, again, to exemplify what kind of things we might subsume under this notion of the perceivable universe. And the important thing again is that no sensory system, biological or technical, can record everything. Right? So either there are things out there in the universe that we just have not seen yet because we don't have the technology to observe them, or in another sense, the universe is actually way too complex for us to really, at a specific point in time, describe it in its entirety. This, of course, it almost goes without saying. But look at this, the human eye, for instance, which we would think of one of the most prominent sensory systems we can probably think of, really basically is confined to just a very small band of electromagnetic waves. We cannot see ultraviolet light, we cannot see infrared light, unless radio frequencies, you cannot see gamma rays, all these kind of things. Our eye, by sort of biological design, is in fact a sensory system that is confined to a very, very narrow aspect of what we call, or what we would call, stuff that is visible. Right? We can create technical sensors that see more, but again, these technical sensors are again not able to see everything. And this is where this with respect to perception comes into play. Right? We have to be aware of the fact that we can basically only recognize what we can perceive. And here is the next thing. Now that we have this one of our bags, this definition of the perceivable universe, things are not basically not much more precise, but we will now build upon what we have seen so far, and so therefore it becomes more specific and less fuzzy. A problem domain, and I shall call it omega. This is the Greek letter capital omega, contains objects, functions, from a specific application area. And note that what has happened here, that the H has switched to a G. And I've done that on purpose. So we can think of the notion of a problem domain as being a subset of the perceivable universe. For instance, if we were talking about stuff I can record with a digital camera, then that is definitely a subset of all the stuff I could record. Right? For instance, if we were to assume that that camera could not record sound, then it would exclude a large part of the perceivable universe already. Right? So a problem domain, say all the pictures in the world, is a subset of everything we can perceive. And I am indicating that by the fact that I've used sort of a specific kind of function, which again indicates a kind of measurement. So it's not an H anymore, it is now a G. And note this, and this is again, this is so abstract, but what can we do? Probably I should have gone back to sound. When we measure sound, then that is something that evolves over time. In a sense, it is something that is univariate. It just depends on one parameter, that is time. So with respect to sound, we would have at every instant in time, whatever our resolution is, one measurement. And say if we were to record color images, and those of you who have been with me before know that a color image consists of basically 3 planes of colors, one for red colors, one for green colors, and one for blue colors, and so on and so forth. So this is just to say that measurements we can make can be of different nature. They may be univariate or multivariate. And with respect to the problem of sensory perception, we could say that this class would contain types of measurements where we have just one measurement at, I don't know, some point in time. And for color images, for instance, we would have several measurements, of course, simultaneously at every point in time. And the elements of omega is of that problem domain we are interested in. Say we want to do acoustic analysis. It's a specific domain within the universe. The elements in omega are called patterns. And from what I have said on the previous slide, we can now realize that, according to our discussion so far, and for everything that is to come, a pattern is a function. Right? So this is where it begins to become mathematical. When we are talking about patterns, from now on, we think of those as something we can describe mathematically. Images can be understood as a mapping from the 3D world that surrounds us to an image plane. Sound recordings can be understood as another type of mapping from the 3D world that surrounds us into well, temporal signals. And these recordings for a specific domain are patterns, and we think of these patterns as mathematical functions. Here are those examples. If we were to record sound by just a single microphone, then the pattern would be a function g of t. If we were to record a gray value image, density image, an image where there's no color in it, we can think of it as a function defined over a plane, so say a function g of x and y. And if we were to record a TV signal, this time with color, basically it would consist of a vector of functions, like something like this here. Look at this, a vector of functions, where we have one part of the signal recording the amount of red light, one part of the signal recording the amount of green light and blue light, so 3 different kinds of measurements. And of course, in a video, we are talking about lots of pictures, so functions of x and y, just as the gray value images, but they evolve over time, so therefore these are actually functions of x, y, and t. And again, all of this is basically mumbo jumbo. It is just to say that this formalism we are walking through at the moment indeed makes sense if we would want to really think in terms of this formalism. And the mumbo jumbo part is here. I have now sort of defined the notion of a pattern, right? And it says nothing. I mean, this is a function of something out there we can perceive. But that is the best we can do. This is fascinating because we can easily discuss patterns. In each of our brains there is, we call it a concept, some idea as to what patterns are. And we have now maybe seen another idea for the first time in our lives, say. And it is fairly precise. From now on, if somebody were to ask you what is a pattern, you could, say, well, it's a function in a problem domain, which is a subset of the universe. which is the entirety of everything that can be recorded. There you go. Right. But what does it say? Not much. But it is the best we can do. This is in a sense at the boundary between mathematics / computer science and philosophy. Right? Philosophers may have deeper explanations as to what patterns are. I do not, and this is the best we can do. But it just goes to show that if we would really want to, we could try to be mathematically precise. And by that, I mean more precise than in the couple of quotes we saw last time. All right, then what is pattern recognition? Right. And again, I call it a definition, so it's in the spirit of the quotes from last time. Pattern recognition deals with mathematical and technical aspects of processing and analyzing patterns. And again, this says nothing. Pattern recognition maps signals, measurements, or patterns to symbols or data structures. See example of that later. And therefore classifies them. Now let's see what that may mean. If we agree again that patterns are functions, some functions, really not very specific here, but some functions, and we are given these kind of things, then what pattern recognition does is it may map the pattern to a class. And I will denote classes throughout this course, again using the Greek letter omega with the subscript I. So for instance, in this lecture room, we could say there's at least two classes of people, female students and male students. And in that sense, we would have omega 1 and omega 2, or omega female, omega male, whatever. You know, this is a class. We could also map patterns to tuples of classes. I could take a picture of all of you guys, and then I could take a picture of the projection here, and then I could try to classify the content of these pictures, like these two patterns, one pattern, second pattern. And in this pattern over here, I could map classes to certain aspects of the pattern, and you would of course agree that if there are these two classes of students in this lecture room, I could map this pattern, picture of all of you, to several classes. And of course we can sort of map pictures, say, to a class, a location, orientation. This is very interesting for robots, autonomous robots that have to navigate in the environment and have to sort of record the environment, however they do that, and they have to make sense of what they record, where they have recorded, and what sort of their viewing direction or location in space was. Well, we can also map patterns to symbolic descriptions, and that is what we are doing in our daily lives all the time. If I were to ask you what's going on in this room, you would say, yeah, it's 10:30, lots of students listening to this pattern recognition lecture, professor stands in front of the projection, blah, blah, blah. It's a symbolic description of what's going on here. Right? And again, we could continue, these are just examples. This is the first thing I would say that is really useful to us for the things that are to come. So the first thing that is concrete enough for us to work with. Here I define that classes or categories result from decomposing omega, is the problem domain we are dealing with, into k or k plus 1 subsets. And these subsets are supposed to be non-empty, so we do not want to have a class where there is nothing in it. Every class we are talking about, a subset of the problem domain, should actually be should contain something. And the next one is not set in stone, but we will sort of require it throughout this course, that any two classes are disjoint. Right? So with my binary example of female and male students, we would assume that there is no student in this room that belongs to both classes at the same time. Right? They are disjoint. And we also want that the union of all the subsets of the problem domain actually creates the problem domain. Or, and this is crucial, I said k or k plus 1 classes. So we are talking about classes omega 1, omega 2, all the way up to omega k. There can be lots of things. And sometimes we also want to have a class omega naught, where the I is 0. So either the classes with an index ranging from 1 up to k should make the problem domain, or sometimes there is an additional class which is called omega naught, but again in these cases the union of all those classes should basically give us the problem domain. Now why would we need k plus 1 classes? Does anybody already have an idea? Okay. Let me first answer that question. What is this? What number is this? 1, 7? Is that so? This is actually a really important problem that occurs to me whenever I have to correct your exams, because some of you have a matricular number where there is a 7 in it, and sometimes you write it in a way that I cannot recognize as a 7. And please, I encourage you really to, I don't know, put a vertical bar here if it is a 7. Otherwise, I'll read it as a 1. All right? So, no, there are patterns for which it is not entirely obvious for us to what class they belong. And in that sense, this is actually why pattern recognition is interesting, or it's difficult, why it is really not straightforward to do it on a computer. And the patterns that are ambiguous, for which we do not want to say, well, this is a 1 or a 7, because it can be both. If we do not want to commit, then it is a good idea to have a huge class of stuff that contains everything we cannot really decide. Right? And it is usually called the rejection class. This is not because we sort of don't like those things, it's just that we cannot classify them into one of the classes omega 1 up to omega k. Right. And the problem here is that whatever makes a class is that we assume that the members of a class are similar. Right? And say we have the class of digits 1 and the class of digits 7. And these guys here, we can, I guess, all agree, are similar to the digits in class 1, or to the patterns of the class digit 1, as well as to the patterns in the class digit 7. And ideally, patterns from different classes would be so dissimilar that we can easily assign them to either class. And when that is no problem, and when that is indeed doable, then it is enough for us to consider just k classes and assume that the entirety of the problem domain can be divided into k subsets if the problem domain is all the handwritten digits of the world. There should be 10 classes, digit 1, 2, 3 up to 0, or 0, 100, and so on. 10 different classes, but sometimes there are these cases for which it is difficult to assign them anonymously to a certain class. Yeah.
How would you train for the rejection class?
We are not there yet. He's already asking about like, okay, how would we do this automatically? Short answer to that question, just because you asked it, is we don't do that. We have it anyway, and we'll have to refine our decision rules when it comes to that. We have to sort of think about probabilities of something belonging to a certain class, and if that probability is not high enough, we do not assign it to the class, but move it to the rejection class. Right? Basically say this is something that is undecidable. And indeed, this problem once again frequently arises in practice, so those of you whose matricle number contains a 7, be aware of that, right? Otherwise, there's always a delay with your grades. And on we go. Even more definitions. Classification applies to simple and complex patterns. A simple pattern is basically if we, these things here, well, they are ambiguous, but they are simple because here we just want to say, well, it's either digit 1 or 7. We just want to assign these patterns to 1 out of 10 or 11 classes. If we were to ask, well, I don't know, how many vertical and horizontal bars are in this pattern, there's a different kind of classes we could ask for, then it becomes a complex classification task. That is to say, we would assign different classes, say vertical bar and horizontal bar, to these patterns. It's just a very contrived example, right? But the take-home message here is either the pattern will in its entirety be assigned to a certain class, or there are several classes we can assign to a pattern, and whether or not we do that depends on the application context we are dealing with. And here is an example. A simple classification problem is, what animal is this? Elephant, yeah. And a difficult or complex classification problem is, what's going on here? Yeah, the elephant is drinking. Actually, there's a very funny story with this picture. It was taken at some day, I don't know, 5 o'clock in the morning in a wildlife resort somewhere in Africa. I forgot where it was. It was a luxury lodge where there are these jacuzzis on the porch. And what is a jacuzzi? Interesting pattern recognition problem. It's either a very small swimming pool or a very large bathtub, you see. But they have these jacuzzis in this resort, in this lodge. They have the jacuzzi, and one of them was losing water. And the janitor couldn't find a hole. It just couldn't, explain how it was that every morning that thing was basically empty. And one day, a tourist staying in that room at 5 in the morning took the picture of this guy. This is one of the elephants in that park, and apparently he came there every morning to have a drink. So this is what's going on in this picture. See, that can be a very complex process to come up with sort of complex descriptions of what's going on. And now that we sort of clarified, is probably a euphemism here, but say that we have clarified what patterns are, what classes are, and what classification is. We can now approach the problem, okay, under these prerequisites, then what do we need to automatically classify patterns? So what I'm going to discuss next are the requirements for automatic pattern recognition, right? And this is now way more important than the stuff we talked about earlier. It's because it's so fuzzy anyway. But and it still looks very fuzzy. But despite its fuzziness, we can make that very precise once we actually work with these kind of things. The most important postulate, something we do require by all means when we want to do automatic pattern recognition, is that there is a representative, and I'm not discussing this notion yet, labeled sample of tuples. And each tuple consists of a pattern and a label. And so therefore, you have a question?
Yeah, when we were talking in the first lecture about pattern recognition, one of the tasks was clustering,
Yeah.
clusterization.
Yeah.
But clusterization without labels.
Yeah, that's true. And it's not pattern recognition in the sense we are talking about right now. Clustering is, again, philosophy. Is clustering pattern recognition or not? If I put on my pattern recognition hat, I'd say clustering is not pattern recognition. This is probably a problem more from the more general question of data mining. Right now, this is about assigning labels to classes or to patterns. Labels to patterns, and these labels indicate classes. This has nothing to do with clustering. Right? For pattern recognition, in the sense that we do want to assign names to things, and we want to assign patterns to classes, we require that we have, at some point in time, a representative labeled sample, where again, the first component of each tuple is a pattern, and the second component is a label. And here is such a pattern. Could be a picture of an animal. It's definitely a pattern in the sense we talked about patterns so far. So this crazy notation thing here, superscript J, G of O, refers to this. And the Y subscript J could be the name of the animal. I guess this is a cheetah, I don't know. Or it could just be a number if, in a more abstract approach to all of this, we'd say, okay, we're interested in recognizing 50 different animals. They, of course, have names, but we could also say the animals in class 1, the animals in class 2, and so on and so forth. So whether or not those labels are words from the natural language we would use to describe the content of that pattern, or they are more abstract things such as numbers indicating a class, it does not matter, right? And here is the second postulate. We require that a pattern has features. And these features are supposed to be characteristic of the class or classes we are thinking about. And here is an example. This is not necessarily stuff we can make out of pictures, but a cheetah, as shown in this picture pattern here, is something that is spotted, very fuzzy, right? Lots of things are spotted, and can go fast. Very fuzzy, lots of things can go fast. But if we are thinking about cheetahs, we try to do that in characteristics. We know about these things, these guys, these objects in the universe. And being spotted and able to go fast are features of the object in the class cheetah. Right? Of course, those are features of many other things as well, but this is an example. And again, we can think of this from the point of view of mathematics. We can think of features as something that results from applying a function to a pattern. Right? So here we are given a certain pattern, and then we apply yet another function to this function, and say it gives us a number of numbers, a collection of numbers, and we will think about these collections of numbers as being vectors. So we are given a pattern, and that pattern can be this, and this is a digital image, and therefore consists of a lot of pixels, and each of these pixels is typically represented in terms of 3 numbers in a very large chunk of memory in our computers. So the pattern is a lot of numbers already, but when we think about features of patterns, then they are something we can derive, extract from those patterns. And note again that I'm really not very specific here. I just say a feature is, or there's a function f that extracts features from patterns. And now we also require, and this is really more or less technical convenience, that features or patterns, and from now on it may happen that I use these 2 terms synonymously. So don't be alarmed. Features of patterns of a class form a more or less compact region in the feature space, if we think of the features as vectors in some higher dimensional vector space. And features from different class, or features of patterns from different classes, are supposed to be residing in other regions of the feature space. This is, again, a mathematical convenience. And look at what that may mean. In this example, I have used a feature extraction function that produces 2-dimensional vectors. And this is, of course, I didn't really do that, I just plotted 2-dimensional figures here, right? But you can think of what this figure shows as the outcome of a feature extraction process, and apparently I have applied this feature extraction process to patterns from 2 different classes, a class omega 1 and a class omega 2. And the way I am showing this picture to you indicates that indeed this is the perfect embodiment of these 2 postulates we would have with respect to features when we want to classify them. They are sort of the features of either class reside in more or less compact regions within this 2-dimensional space, and the features of the 2 classes are rather well separated. All right. This is the ideal setting for pattern recognition. Say we are given 50,000 images, 25,000 of those images are of cheetahs, and 25,000 images are of elephants. And we have a pattern recognition function that would measure the ability to go fast and the ability of not being spotted, or the fact of not being spotted, right? Then all the cheetahs, as they are spotted and fast, would be here, at least their features. And the features we extract from the pictures of animals that show, or pictures of elephants, would reside here. Lots of pictures, and we have sort of condensed them into 2-dimensional vectors, and now we are dealing with this feature space, and our task in automatic pattern recognition would be now to decide if there is a new image coming in, we would extract features, and that feature vector would land here. Then our task is it to decide, is it a cheetah or an elephant? Okay? And in this case, this would be fairly simple to do. We could, for instance, try to determine the distance between the new, like make it here, the new feature vector and all the feature vectors of the elephants and all the feature vectors of the cheetahs, and just go for the class where the distance to the other examples is smallest, right? Or we could be a bit more ambitious and say, well, if we look at this, we could draw a line here, and everything on this side of the line would be called an elephant from now on, a member of class omega 1, and everything on this side would be called an element of class omega 2. And maybe if it so happens that there is a point that would end up exactly on that line, however we get this line, then is of course sort of an element of both. Gets back to your questions, we would not have learned that, but it would have sort of the same probability or likelihood or indication of being an element of both, and in those cases we would happily make use of the idea of a rejection class. Right? Now this looks very simple, but of course in practice features may form different distributions in the feature space. This one is still very simple, right? This is no problem at all. This one is slightly more challenging. Whereas in the first, this is the ideal. This never happens. You will never see that in practice, let me tell you that. This is the ideal case because it's so simple to decide whether this point should belong to that class or that. What is the problem here? And here as well, we can definitely have a line that would separate the two. In the third picture, there is no line that would separate the two. And still, we could probably come up with a function that describes the boundary between these two distributions, between the features, the two classes. So again, this is it's definitely more challenging than these cases, but still not much of a deal. No, we're getting more realistic here. Here we can still think of, I don't know, some crazy function that would separate those two classes, but the functions are getting crazier. And they can be very crazy if need be. Right? And in fact, they can be utterly crazy. And this is reality. Right? And this slide is where everybody should be awake. I told you that I'll point out the points where you need to be awake. This slide embodies our whole course. We are going to study the problem given the features. From now on I will really, again, like I may use the terms patterns and features synonymously, and from now on I will usually assume of them being points in some space, some vector space typically, and I will also assume that we have classes of points, and our problem for the rest of this course will be to come up with ways of trying to determine the boundaries between the points of different classes in some abstract higher dimensional spaces. And seriously, by far the most realistic setting is this over here. We therefore can define the problem or task of classification as the problem or task of mapping features extracted from patterns to classes. Right? And again, like whether we extract features from a pattern or we try to map the pattern directly, I will very likely use the terms features and patterns synonymously now. But you know that if I were to be precise, I should distinguish those. But I'm sloppy, right? So don't be alarmed. Yeah, we have already talked about the fact that a pattern may be simple or complex. That is the question, are we going to assign names of digits to binary pictures as we saw earlier, or are we trying to describe these binary images in terms of their components, vertical and horizontal bars and arcs and whatnot? And if a pattern is complex, we say that it consists of elementary components, but this is not in a random fashion. there are relations or configurations in to which these components have to adhere. And again, this is best described in terms of an example, and again, because I'm using slides and can only show sort of two-dimensional things. What is this? This is a street scene. How are we able to recognize that? Well, cannot really answer that, we just see it, but there is something we would call a street. There is something we would call a sidewalk. There are things we would refer to as pedestrians. There are things we would call cars, and there are houses. And if one of the cars was up here, and one of the pedestrians was lying over here, and if one of the houses was turned sideways, and again, like then it would be way more difficult for us to say this is a street scene. Why? Because this is a complex pattern that consists of simpler patterns or elementary parts in a certain configuration. And these configurations, of course, are very flexible because there's nothing that would prevent the pedestrians from walking on the street or the cars from parking on the sidewalk. But there are certain relations we could expect to find in complex patterns. Again, it would be very, very unusual if one of the cars was hovering up here. Maybe in a couple of years, but right now it's very unusual. And so therefore, not every arrangement of elementary components would form a valid complex pattern. What else do I have here? And this goes back to one of the things I mentioned earlier. I said stuff we can do with patterns is to assign them to classes or to come up with symbolic descriptions. And I also said we may assign them to data structures, right? And this is an opportunity for me to have an example as to what that may mean. We could, if we would really want to, I actually don't want to, but we could describe this pattern in terms of a graph. We could map it to a graph. We would say we have vertices in that graph, a mathematical graph, vertices and edges between those vertices. And say for every sub-pattern in this pattern, for instance the pedestrians, we would have a vertex. And other sub-patterns would be the cars, and we would have a vertex. And we would have a vertex for street and a vertex for sidewalk. And then we could draw edges between these vertices that would indicate relations between objects, patterns, sub-patterns in the scene. Say we would have a vertex from pedestrian 1 to sidewalk, and this an edge, and this edge could be labeled with on top of something. So if we really would want to, which I don't want to, but we could map this pattern to a data structure. All right. This is an example for what I mentioned earlier. And if we do this, then the resulting data structures are either valid or not. We can use these graph-based representations of complex scenes. We could use them to decide whether or not that complex scene is a valid pattern. Yeah, and here is the notion of similarity again. In order for us to be able to automatically do pattern recognition, we postulate, that is, we really require that patterns from the same class are similar in the sense that their features or elementary components do not differ much. This is otherwise, if that is not given, then pattern recognition will be more or less impossible for us to do algorithmically. And now, here is the thing that does not make a lot of sense at this point in time, but I thought, since I have been talking about all these elementary things and basically The purpose of today's lecture up until now was just to throw all these terms, universe, problem domain, class, pattern, feature, all these things, I will use them from now on, and now you know what I mean. That was the purpose of today's lecture. I'm basically done with this, and since there is some time left, I thought, what else can I do? And what we're going to do now is I am walking you through the process of building an automatic pattern recognition system. And of course, I will not whatsoever discuss any details here, but just point out the fact that the process of building an automatic pattern recognition system typically consists of 3 disjoint phases. And usually I never mention this so early in the lecture, and I had to pay the price for that later on, and I'll tell you why once we come to that point. So, having defined what pattern recognition is, has to do with problem domains and classes and patterns and features, and then having defined what we need to do or to have in order for being able to do it automatically, like labeled samples of patterns from different classes, and those patterns or features we extract therefrom have to be similar for individual classes, blah, blah, blah. Having defined all that, here is, from a very general point of view, the process of building a classifier. It typically involves, let's say, 3.5 phases. Given a labeled sample of patterns or features, we will use them to train a classifier. And once we have trained a classifier, and this is the main question of this whole course, once we have trained a classifier, we may want to evaluate this classifier. See, like, how good is it? Is there something we could do about it? Those are the first 1.5 phases of building a pattern recognition system. Once we have trained and evaluated and probably adapted our classifier, we can now test it. So there's a difference between evaluation and testing. And once we are happy with the test results we get, we can roll it out and use it in practice. And in the training phase, so the training phase consists of these couple of steps. So we first collect a training set of patterns, and we label them. So if you are lucky, you are dealing with a practical problem where you have labeled data at your disposal, but as you are students, most likely you will not be dealing with these kind of things like doing your, say, master thesis or PhD thesis. Most important job of students in this area is actually to label stuff. But in order to build a classifier that helps us with a certain problem we have, we need data, that is a collection of patterns or features, and somebody needs to sit down and assign labels to that data. And we collect the labeled data in the so-called training set. Yeah, then maybe we have this process of feature extraction. And now that we're given the labeled patterns and have extracted features, maybe we can create a plot, some visualization of those features that would provide us with an intuition as to what kind of mathematical model we can now use to actually try to distinguish features. Let me go back. Here, for instance, here basically we can use everything. Like, say, if I were able to create this plot from the data I'm given, I'd say it doesn't really matter. Any classifier will do. Whereas here, for instance, say, okay, I can forget about the idea of finding a linear classifier. Maybe I should use a so-called nearest neighbor classifier, or I don't know, some support vector machine or something like that, right? Just from looking at if it is possible for us to have a visualization of the data we are dealing with, we can then decide what kind of approach to use. Sometimes it is of course impossible for us to plot that, but maybe there is additional information we have about the problem we are dealing with. So every information we have that could inform our decision what to do with the data we are given is useful to be evaluated here, right? Because we need to determine a mathematical function, let's call it y of x, that maps the training data to its labels. So our goal is to find a function y that, given one of the features in our labeled training sample, produces the corresponding label. Right? And there are of course numerous possible functions we could use here. This course is about all these functions. Say we have decided for such a function and we have trained it on the data. That is to say, we have determined suitable parameters of our mathematical model such that it produces labels given a feature. We can then look at how good it does so on our training set. And typically, in order to do this correctly, we would require that the data set on which we evaluate the performance of the classifier we trained in the previous step is disjoint from the set we used to train the classifier. And we have trained our classifier on this data here, and it produced some function, and now we evaluate the performance of how often is it correct, how often does it make a mistake, stuff like that. There are several measures we can think here called, say, accuracy, precision, recall, all these kind of things. Can evaluate it on this other set and find that it does a poor job. If that was the case, then we might think about readjusting our classifier. Do some more training, probably with more data. This is the half phase in the 1.5 first phases. This is not really necessary. What is necessary, however, is now for real, right? I said, okay, we evaluated the performance of the function we trained in order to use it as a classifier, and then we, given the results of that evaluation, retrained it or whatever. But now that we have decided, okay, this is going to be our classifier, now we have to evaluate it for real, to test it. And to this end, we collect another data set of patterns from the same domain, and somebody has to label it. And look at this. This time I emphasize it, bold font and in red. Here I didn't. Okay? But here I do. In this stage of the construction of an automatic classifier, it really has to be the case that the test set is disjoint from the training set. And this is basically the reason for me to talk about this at this point throughout the course. Right? I always thought this is self-explicatory, but of course at some point in my life I learned that as well. And I always sort of just discussed it towards the very end of the course when it was too late, when you had done your projects already, and evaluated the performance of your stuff on the training data. Now, this won't do. For statistical reasons, which we will discuss later on, these two things have to be disjoint, right? So you have trained your classifier, and now you want to roll it out to a customer. And they will want to ask you, so how good is it? Right? Can we trust it? Can we base business decisions on your classifier? And then you can say to them, yes, we evaluated and it gave a performance of 96% accuracy, something say, right? That would be good. But when you tell them that this 96% accuracy has had to be measured on a data set that is independent from the set you used for training, right? All the patterns in here, of course, have to be similar to the patterns you used for training, because otherwise it could not work, this whole mechanism. But none of the patterns in here must be in here, or if you throw dice, then like you will see lots of sixes in here and there. But the way you acquire this data has to be independent from the way you acquired that data. And you have to report the quality of what you did based on measurements you did here, right? And this, of course, will happen in the project. Yeah, how do you evaluate? I say objectively evaluate this. There are a couple of numbers you can compute automatically. These are called accuracy, precision, recall, F1 measure, and so on and so forth. We will talk about them in due time. And now, in the application phase, you roll it out to your customer or for whatever application you need it, right? And I say if the classifier meets the quality requirements, then apply it in practice. And this, at this point in time, is again a very loose thing to say. The quality requirements you would ask from an automatic classifier very much depend on the application it is intended for. Consider, for instance, the problem of monitoring an atomic power plant for potential accidents, right? And so there are lots of sensors in the atomic plant measuring temperature and water pressure and what else, like lots of stuff, patterns. And we can extract features from them, but say the measurements are the features already. And we could assign labels to these measurements, to these patterns, to these features. And the labels could be everything is peachy, everything's okay, I don't know, critical development or accident imminent, something like that. Or it could be a binary decision, everything's okay, and abandon all hope. And you have trained a classifier, and in that setting, it is very likely that the majority of the data you will obtain from practical measurements would indicate that everything is okay, right? Like, because one would hope that critical situations in atomic power plants don't happen too often. So your training sample could be very much biased. Say 98 out of 100 patterns would correspond to a situation where everything is okay, and only 2 of them would correspond to a situation where an accident is about to happen. Now, a philosophical question is this sample representative or not? It is probably representative from the point of view what is usually going on. Hardly ever any accident. But with respect, say, to automatically learning about what distinguishes situations that are not worrisome from rather worrisome situations, it may be the case that your training data did not contain enough examples of problematic situations. So it's an argument, is this representative data or not, right? But let's not look under that rock. Say you have trained a classifier and it has an overall accuracy of 99%, 98% say. And that is to say your classifier has learned to correctly identify the cases where everything is okay, but looking back at this, where is it? This one here, you know, classifiers may make mistakes. Instead of labeling this point as a member of omega 2 class 2, it could probably, for whatever reason, have learned a function that would say this blue point here is actually member of class omega 1, orange point. And in your atomic power plant classification setting, you have found a classifier that has almost perfect performance in the sense that it recognizes all the usual cases perfectly, but makes 2 mistakes out of 100 cases. Accuracy of 98%, but those 2 mistakes are the ones where an accident is imminent. Now we could be tempted to say, well, this is a great classifier, accuracy of 98%. That's of course exactly the opposite of what we would hope for if we were to use an automatic pattern recognition system to monitor an atomic power plant. It would definitely have to be the other way around. Right? We could never afford to make a mistake on the critical events. However, it would be an annoyance for the people working there if there are a lot of false alarms, in the sense of your classifier would say, hey, this is critical even though everything is okay. Right? But because they would have to check it, and that could, you know, but that would be in this setting, that would be okay. And the other way around, you cannot afford that, right? And this is what I mean with meets the quality requirements. So it is a fallacy just to say, yeah, the accuracy of this thing is so and so. That can lead to a situation that is actually still exactly the opposite of what you really want. And you have to be aware of that, right? That the evaluation, so whatever you do here, when you evaluate the quality of what you do in pattern recognition, it has to be with respect to the problem you're dealing with. And if you read the literature, this aspect is basically overlooked these days, because most of the literature out there deals with, is this an elephant or a cheetah, stuff like that, right? Like it's very difficult to automatically recognize the content of images, but there are not many practical applications where we need to automatically decide whether it's an elephant or a cheetah. And most of the situations where all of this is used in practice are more of this nature. And so therefore, now you know all this. You know that you have a training set used to train your classifier, and then you have to test your classifier on a test set that is independent, and it has to be, it must be, everything else leads to failing the course. Must be independent of the training set. And whether or not you evaluate with accuracy, with respect to accuracy or precision or recall, needs to be decided in the context of the problem you are dealing with. Right? And now you know all this already at the beginning of the course, and so therefore do it like that. Right? And therefore, today we have learned about at least an attempt of trying to formalize the notions of problem domains and patterns, classes, features, and classifications. And by far the most important thing we discussed today was the question how to build a pattern recognition system. And of course, no details there whatsoever, but at least the flow of the process, the bigger picture is there. Right? You now know that there's 3 or 3.5 phases: training, testing, and application, and how to deal with these phases. This is everything I have for today. Next time we will finally begin to acquaint ourselves with the mathematics we are going to need for this. I'll be talking about linear algebra. After that, we will be talking about basic probability theory. After that, we will be talking about how to compute with probability distributions, and then we will begin to use these things we are going to learn about next time for pattern recognition algorithms. Do you have any questions? No, if not, then thank you, don't run away. I have two.